At the end of the last video, I presented to you these different types of levels of measurement: nominal data, ordinal data, interval data, and ratio data. But I want to go through them one more time here because we'll use this for our next example. So levels of measurement data may be classified according to the following levels. Nominal data consists of names, labels, or categories. There is no natural or obvious ordering of nominal data, and we cannot carry out arithmetic. Or we could have ordinal data. Ordinal data can be arranged, unlike nominal data, which has no natural order. The ordinal data can be ordered, but we still can't perform any arithmetic. Or we could have interval data, which can be ordered, just like the ordinal data, but with the extra property that we can carry out some arithmetic. We can do subtraction, but there's no natural zero for this data. Or we could have ratio data, which, like ordinal data, it can be ordered, and like interval data, you can do subtraction, but now we have one extra property. You can also do division, and we have a natural zero. So we'll do an example, and it should become a little bit clear what we mean by these things. We have a question. We want to identify which level of measurement is represented by the following data. And the answers are already here. The years 1066 to 1492 represent interval data. There is no natural zero, and division doesn't make sense. 1492 divided by 1066 doesn't make sense. However, we can do subtraction. We can do 1492 minus 1066 is equal to 426. Let's try to get a minus in there. Minus equals. So there is arithmetic that we can perform. Okay, what about another example? The annual income of students in a statistics class. Between $0 and $15,000. So student income represents ratio data, because here it makes sense to do division. For example, if someone made $4,000 last year, then they made twice as much as someone who made $2,000 last year, or 4,000 divided by 2,000 is 2. So that's the example of the division we can do. Also, some students probably had no income last year, so $0, no income, is a natural zero that makes sense. Another example could be course grades in an English class. A, B, C, D, or F. Course grades will be an example of ordinal data. Because we can't perform any arithmetic, you can't subtract A and B, it doesn't make any sense. You can't divide F over C, that doesn't make any sense, but there is clearly an order. Getting an A in a class is better or more desirable for the student than getting a C in a class. So we can order them, but we cannot perform any arithmetic. And finally, what about student gender, male or female? This would be an example of nominal data because there is no way to do addition, subtraction, division, multiplication, and there's no clear order. There's no obvious way to say male is better than female or female is better than male. They're just two different categories. So this is what we call nominal data. So these are good examples for you to go back and think about when you're trying to understand what might be called ratio, interval, nominal, or ordinal. Example, identify the variables that represent the following levels of measurement. We said that nominal data might be something like gender or some other category where there's no clear ordering. Ordinal data might be something like grades where there is a clear ordering, but you still can't do arithmetic. Interval data, something like years, because we have ordering, which came first and which came later. And we can do some subtraction, like the number of years from 1066 to 14 whatever. But we can't multiply or divide. That doesn't make much sense. And then ratio data might be something like income, because there is clearly an ordering. $4,000 is more than $0. We can do subtraction, division, multiplication, addition, and all of those things. Okay, so next thing, we'll talk about statistical inference versus inferential statistics. Not versus, but statistical inference and inferential statistics. Inferential statistics use methods that take a result from a sample and extend it to the population, and then measure the reliability of the results. So it might not be feasible to collect information about every single thing in a population. We'll take a small sample, and then we will extend what we see in the sample and say, maybe that's true for everyone or everything, but we can't know for sure because we didn't take the measurements for everyone or everything. So then we want to measure how confident can we be, how reliable is this conclusion. So that's what we mean by statistical inference. A parameter is a characteristic of a population. A statistic is a characteristic of a sample. So we have summary and attributes of statistical samples. Another table here. The population versus the sample. And so just a brief definition, the population is all elements, whereas the sample is a subset of the population. And remember, we said the subset of the population could be the whole population. A characteristic of a population is a parameter, whereas a characteristic of a sample is a statistic. The value of a parameter for the population is usually unknown, because as I said, it might not be possible to take a measurement for every single item in a population, whereas the value for the statistic, for the sample, is usually known. And the status, when you take a sample, we say it depends on the sample, because depending on which sample you take, you could get different results. And that's what we talk about when we say we need to measure how confident we can be or how reliable our measurements are. Whereas if you take the measurement for the population, you should get the same measurement every time, so we say it's constant. So this is just sort of a summary of the difference between population and sample. Let's look at an example. We want to identify the population and the sample in each of the following. 1. A researcher is interested in the median home sales price in some county in Texas. He collects sales data on 100 home sales. So we want to know, what is the population? In this case, the population is the thing he's interested in. Median sales price in Texas. So the population is just all home sales in Texas. In Tarrant County, I should say. Whereas the sample is going to be just the data he collected for 100 sales. All right, what about a psychologist is concerned about the health of veterans returning from war? She examines 20 veterans and assesses whether they show signs of post-traumatic stress disorder. So in this case, the population that she's interested in is all veterans returning from war. And the sample is just the 20 veterans that she collected data about. A sociologist wants to learn about the number of meetings per year of 4-H clubs in Maricopa County. He collects information from 10 different 4-H clubs in various parts of the country. Our population here is all 4-H clubs. And our sample is just the 10 4-H clubs which we collected data about. All right. Another example, state whether descriptive statistics or statistical inference was used and explain why. The average price in a sample of 15 homes sold in Jacksonville, Florida for the week of April 21st was $253,200. This should be descriptive statistics. Because we simply took some measurements of a sample and we described that sample. Let's go back and remind ourselves of the definition of descriptive statistics. Descriptive statistics consists of organizing and summarizing data. Descriptive statistics describe data through numerical summaries, tables, and graphs. And so that's what we have here. The second example, according to the Department of Transportation, 60% of all automobile passengers wear seatbelts. This is based on a survey of 1,000 automobile passengers, of whom 600 wore seatbelts. So this is going to be inferential statistics. Now let me actually write, because we're supposed to explain why. This is inferential statistics. Because data from the sample of 1,000 automobiles is being used to describe the entire population. The Department of Transportation says that 60% of all automobile passengers, so they're taking the 60% from their sample and they're expanding that to say this should hold for everyone. So for number one, we said this is descriptive statistics because data from the sample is only being used to describe the sample. So if you had a question like this on a test or a quiz, you would want to write a sentence like this. It doesn't have to be this exact sentence, but you would want to explain the difference between the two. A third example, in a sample of 500 subjects, it was found that daily exercise lowered the average cholesterol by 10%. A medical spokesperson then stated that daily exercise can lower everyone's cholesterol by 10%. So just like example 2, this is inferential statistics or statistical inference. And again, for the same reason, because data from the sample of 500 subjects is being used to draw conclusions about the entire population. The medical spokesperson said that because we took a small sample of 500 people and we found it to be true, we can assume that it's true for everyone. That's not necessarily true that we can make that assumption. That's where measuring our reliability and our confidence comes in, which we'll get to much later in the course, but we just need to understand the difference between descriptive statistics, like in example 1, where we collected a measurement and we used that data just to talk about the sample, versus inferential statistics, where we collected a measurement and then we used that data to extrapolate into what might be true for everyone or everything. Oh, one more example. In a sample of 140 traffic fatalities in New York, 75 involved alcohol. So this is like number 1. This is descriptive statistics. Because we just collected measurement from a sample, and then we talked about the implications for the sample. Data from a sample is used to describe only the sample. All right, so here we have a table, crime statistics in Stillwater. We want to refer to the following table and then complete A through D, and provide the observation for motor thefts. So first, let's familiarize ourselves with the table and see what it's telling us. So we know that this is crime statistics. And across the top, the first row, we see the columns are titled crime type, 2005 total per 10,000 people, national per 10,000 people, and compared to national average. So this first column, crime type, these should list our elements. And this first row should be our variables. So A, list the elements and the variables. Elements are going to be robberies, assaults, burglaries, and motor thefts, larceny. So different types of crimes. And for each type, or for each element, we're going to measure these variables. It looks like the variable should be 2005 total per 10,000 people. National per 10,000 people. And compared to national average. All see what B is asking us. B, identify the qualitative variables and the quantitative variables. So we'll look at our variables. 2005 total, per 10,000 people, national per 10,000 people, and compared to national average. And we want to decide which are qualitative and which are quantitative. So for qualitative, remember we're looking for a category that doesn't necessarily correspond to a number. So that looks like compared to national average. The last column should be our qualitative variable. And then if we look at the other three, the values are clearly numerical. Number of instances per 10,000 people, number of instances per 10,000 people nationally, total in 2005. So we'll say 2005 total per 10,000 people and national per 10,000 people. These are our quantitative variables. So that's question B. And question C is, for each variable, identify the level of measurement. So again, our variables are the 2005 total, the per 10,000 people, and so on. And we want to determine level of measurement, meaning we want to decide if each one is nominal, ordinal, interval, or ratio. So I'm going to write these down, and we'll see if we can figure out the level of measurement for each variable. Okay, so we have our variables. So let's first look at 2005 total. 2005 total, 10, 83, 317. These are our numbers. I could do subtraction, I think. So I could say there are 73 more assaults than robberies in 2005 by taking 83 and subtracting 10. So it seems like it should at least be interval data. But I could also compare 83 divided by 10. There are 8.3 assaults for every robbery. So that's division. And so that should be ratio data. What about per 10,000 people? Per 10,000 people, I think I could do the same. Say how many more assaults than robberies, or how many more thefts than motor thefts. And I could also do their ratio for each motor theft. How many burglaries do I have? And I'm going to say it's exactly the same for national per 10,000 people. The only difference between those two columns are we're looking at just in Stillwater for the per 10,000 people, or we're trying to compare to the entire population for the national per 10,000 people. So both of those columns should be ratio data because, again, we can find the difference between two elements, or we could find their ratio. And then finally, compared to national average, it's either better than the national average or it's worse. So it should not be ratio data because there's no way to divide better divided by worse. And it shouldn't be interval data because we can't subtract better and worse. So it's either going to be nominal data or ordinal data. And I would like to say it's ordinal data because I think that I can put those in order. I think I can say that it's better to be better than it is to be worse, or it's worse to be worse than it is to be better, that type of thing. So because there's a clear ordering, I want to be better than the national average, not worse. I get to say it's ordinal data. It has an order. Okay, so that's C. Question D. For each quantitative variable, indicate whether it's discrete or continuous. So we know that our quantitative variables we found in part B are the 2005 total, the per 10,000 people, and the national per 10,000 people. So let's put part D out here, and I'm going to say the 2005 total, the per 10,000 people, and the national per 10,000 people. I want to say whether they're discrete or continuous, and this is going to be question D. Let's take a look. For total, we're counting, right? We're counting there were 10 robberies. We're counting there were 83 assaults. So should that be discrete or continuous? Well, we said that whenever we can count them, and we get these nice whole numbers, 1, 2, 3, 4, 5, and so on, we call that a discrete variable. So I'm going to say my 2005 total is discrete. Let's look at per 10,000 people. Per 10,000 people is like a type of average. So you can see we have numbers like 24.4, 202.4. And if I put a number there that was 202.41, 42, those would all be valid values. So that's what we call continuous, because we can't simply count 1, 2, 3, 4, 5. You can have decimals and every number in between. Between 24 and 25, we can have 24.1, 24.2, 24.3, and so on. So we said, since it can take on every number between any two whole numbers, we call that continuous. And then if you look at the national per 10,000 people column, it's exactly the same reasoning that we would call it continuous as well. So both of these columns, per 10,000 people and national per 10,000 people, we're calling them continuous because they can take any value between two whole numbers, whereas the discrete variable, which is totals, can only take on whole numbers. You can't have half of a robbery or half of a theft. So we've answered A, B, C, and D. And the last thing it asks us to do is provide the observation for motor thefts. So remember, when we say the observation, that means we want to look at motor thefts and try to describe everything that we know about it. So let's go back up and read about motor thefts. So motor thefts is the last row in our table. And we can see that in 2005, there were 55 total motor thefts in Stillwater. So per 10,000 people in Stillwater, that's 134. And nationally, per 10,000 people, you get 526. So Stillwater is doing way better than the national average in motor thefts. So we'll say, in 2005, there were 55 motor thefts in Stillwater. Which is 134.1 0.1 motor thefts per 10,000 people in Stillwater. Nationally, there were 526.5 motor thefts per 10,000 people. So we get to say, so compared to the national average, Stillwater is better. Better because it has fewer motor thefts per 10,000 people. That would be our observation for Stillwater. So again, if you had a question like this on a test or a quiz, you would want to write out just a couple of sentences like this, where you summarize what you read in the table. So that looks like that's everything for this lecture note. So as I said at the beginning of the first video, you'll want to go back now to the objectives at the top of the lecture note and ask yourself if you can define statistics and statistical thinking, explain the process of statistics, distinguish between qualitative and quantitative variables, distinguish between discrete and continuous variables, and determine the level of measurement of a variable. All 5 of these things were introduced in the first video, and in the second video, we did several examples to try to highlight what those things mean.